Hello and welcome to today's video on section 12.6, area and circumference of circles and the number pi. I am Mrs. O'Brien. For any circle, its circumference measured by its diameter is always the same number. That number is pi. In other words, the ratio of a circumference of a circle to its diameter will always be pi. We use pi in many of the calculations we do for circle. For example, the circumference of a circle is 2 pi r, or pi times the diameter, and the area of a circle is pi r squared. We can see why this area formula is plausible in subdividing a circle into pi pieces and rearranging them to form an approximate rectangle or parallelogram. We have demonstrated that in one of our class activities as well as my first example. In this example, this circle has been subdivided into sectors and they've been pulled apart and put together. And these are 4 different representations depending on how many different breaks you do in this. I have an excellent video that I have shared with the class that shows this in action. But basically what I want you to realize is that this segment here, the radius of the circle, is also the side of each of these sectors. So as I make my sectors smaller and smaller, or create more and more of them, we notice that as I put them together, it looks very much like a parallelogram here, and if I cut them tiny enough, it would eventually approach looking like a rectangle. Now this edge here is still the radius on all of them, and that radius is approaching the height of this rectangle. Now you might notice that I went around the circle in orange to show you the circumference of the circle. And I outlined it here on the curvy portion of each sector. So those little arc lengths there that go through combined together would equal the circumference of the whole circle. So if I just look at the top part, that's half of the circumference, and the bottom part is half of the circumference. And that happens on every single one of them. So down here where I have the area for the rectangle, that this segment here, the length of this would be 1/2 c, or 1/2 the circumference. Since I know circumference is 2 pi r, I'm doing half of that. Well, 1/2 times 2 is really just 1. So that gives me pi r times r, which is that height there, and r times r is r squared. So here we are to our formula of the area of a circle, pi r squared. This next example, some trees in an orchard need to have their trunks wrapped with a special tape to prevent an attack of pests. Each tree's trunk is 1 foot in diameter and must be covered with tape from ground level up to a height of 4 feet. The tape is 3 inches wide. Approximately how long a piece of tape will be needed for each tree? Please note in this problem when they say how long of a piece of tape, that is a linear measurement, and a linear measurement means that we're not talking about area and we're not talking about volume. So since a tree's trunk is somewhat circular, we're talking about the distance around a circular tree. So here I have the tree, the distance around the tree trunk, and if it's 1 foot across in diameter, this circumference of this distance around this tree would be pi times 1, or pi. Now, since the tape itself, if we consider this the tape, is 3 inches wide, I have to figure out how many times I'm going to need to wind that around to get to a height of 4 feet. So to do this, I first converted 4 feet into inches. So 4 feet is the same as 48 inches. So if those are 3 inches wide each time I go up, that's 16 times around the tree, or 16 winds that I would need. But I still need to know the distance around that whole tree multiplied by the 16 winds to get the total amount of tape. So I'm going to take my 16 winds, I'm going to multiply it by the circumference of pi. That'll give me approximately 50 feet. So 16 times pi, or 16 pi, is approximately 15 feet of tape that I would need for this example. Again, when you read the problem, ask yourself, are they asking for a linear measurement, a 2-dimensional measurement like area, or a 3-dimensional measurement like volume? In our next problem, the Browns plan to build a 5-foot wide garden around a circular garden. Sorry, they plan to put a path around the circular garden. So this part inside here, see if I can get a little highlighter going on. The part inside here is the garden, and the brick part is the pathway. So if I look at this, the bricks are 5 feet wide on either side, and then the distance across the garden is 25 feet. So the outer part of this circle would be a distance of 35 feet. The 5, the 25, and the 5, so all the way across. But the inner circle, which is your actual garden, is only 25 feet across. It specifically says here we're looking for area, so we know that we're looking for a two-dimensional measurement. As I do this problem, I here have noted that the 35 feet goes all the way across, so that radius would be half of 35 is 17.5 feet. And half of that 25 feet would be 12.5. And the reason why I'm representing the radius on these pictures instead of the diameter is because to find the area of a circle, we're going to use the formula pi r squared. So if the area of a circle is equal to pi times r squared, I need to know the radii of my circles. So if I find the area of this large circle, the outer circle here, and if I find the area of it, that's going to be everything. And then I find the area of the inside circle, that's kind of this light yellow color, and I subtract the two, I'll get the bricks around the pathway. So if I find the large one, that's going to be the 17.5 radii squared times pi. And then the area of the inner circle is going to be the 12.5 squared times pi, which I've shown right here. So this is the area of the large circle and everything inside. And then the area of the garden, which is the inside part here, is the 12.5 squared pi. So if we did this calculation, we end up with approximately 471 square feet for the area of the pathway, which is these bricks going around. In this practice question, it asks what's the area of the 4-petal flower in the figure below. The square is a 6 centimeter by 6 centimeter, and the curves are formed from half circles. So that means the half circles each have a diameter of 6 centimeters, if that is the side length of the square. So in order to find these petals, we're going in the green pieces, we're going to have to do some calculations. And I've made a couple diagrams here just to kind of show you one way you can look at it. There's definitely more than one, but if we think of them as like half circles, and I have a full circle down here split in half, and I put half here and half here, you'll notice that the only thing left are 2 orange pieces. So that would be one way of finding the area, is to do the area of the square, subtract the area of the circle, and that would give you the orange parts that you then could remove from the total. Another way is to cover it, instead of with one circle, go ahead and cover it with a whole nother circle. And I know it's hard to see, but there's an overlap there. And that overlap is where those green leaves are. So this overlap section is that area that we were looking for. So how can we do this? We can find the area of those 2 whole circles, or 4 half circles. And that's the area of the flower, those dark green petals, plus the area of the square. So that means if I find the area of those 2 full circles and subtract the area of the square, what will be left is just the area of the flower, or those green petals. So when I do this, when I find the area of the circle, remember that that diameter going across all the way was 6 centimeters. So that means that the radius is 3 centimeters. So to find the area of a circle, I'm going to go pi r squared, or pi times 3 squared, which equals 9 pi. Now I have 2 of those, so if I multiply by 2, I get 18 pi for the area of 2 circles. Then I also have the area of that square. So the area of that square, remember it had sides length 6, so that's going to be 6 times 6, or 36. So the area of the square is the 36 piece, and then the 18 pi is the area of those 2 circles together. So if I subtract that, what will be left is the area of the petals. Again, that's one way to do it. There's definitely more than one way to solve this problem. Thanks for watching. These images came from our textbook, and most of them are from the practice exercise questions in section 12.6.